Good afternoon, this is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. Today we'll discuss some things about vapor compression refrigeration system. This topic comes under the applied thermodynamics for 4th semester mechanical engineering students. Now, as we have seen in the previous classes, that we have cyclic process, we have non-cyclic process, and other modern trends for refrigeration cycles. Okay, for refrigeration, for producing the refrigeration effect, we have many process. One is some of the cyclic process and some of the non-cyclic process. Now, in cyclic process, we have the air refrigeration systems, and the second one is vapor compression refrigeration system, and third one is vapor absorption system. In previous class, what we have seen is how the vapor compression refrigeration system, we have seen the brief introduction about that. We will recap it a little bit. Now here you can see the diagram here is showing the enthalpy, pressure versus enthalpy diagram. So the y-axis is giving the pressure lines and the x-axis is giving the enthalpy lines. So suppose if I take point 1 here, this gives what is the enthalpy at this point, and this will give what is the pressure at this point. So we have 4 points in this representing this cycle, and because it is a cyclic process, 1 to 2, 2 to 3, 3 to 4, 4 to 1, again like this the process will be conducted in the form of a cycle. Now here at point 2, the vapor is entering the compressor. The vapor is entering the compressor at dry saturated condition. Okay, so suppose this is a evaporation process, this is throttling process, this is condensation process, and this is compression process. So as we have already discussed, the vapor compression refrigeration system have 4 processes. One is evaporation process, compression process, condensation process, and expansion process or throttling process. Now here in throttling or expansion, what happens is the pressure reduces. You can see from 4 to 1, the pressure is dropping. Here it is a P4 and here it is a P1. P1 is less than P4. So it is a isenthalpic. The enthalpy is constant here. You can see here the enthalpy is constant. So it is isenthalpic expansion process or pressure reduction process. So if it is now here what happens is, since the pressure is low, the liquid which is there, it will boil at lower temperatures. Okay, as the pressure reduces, the boiling point of the liquid reduces. As the pressure increases, the boiling point also increases. This is what we use in our pressure cookers. There we increase the pressure so that the boiling point will increase, and because of that the water will stay at higher temperatures, and the food gets cooked. So that is about the pressures at different temperatures. Now here, as we have discussed just now, the pressure is coming down from 4 to 1. Now at the lower pressures, even if I supply little bit of heat also, corresponding to the boiling point at this particular pressure, if I supply the heat, what happens is it will get evaporate, or it will become vapor. Now this dry saturated vapor enters the compressor, and in compressor it will be compressed. Okay, and in the compressor it will be compressed. Compressed in the sense the pressure is increasing. So from point 2 to 3, the pressure is increasing. At point 2 the pressure is P1 and at point 3 the pressure is P4. Again we are going from P1 to P4. So the pressure is increasing. And what type of process it is? It is supposed to be isentropic process. The entropy should be constant but enthalpy will be changing. So it is an isentropic process between point 2 to 3. So here from point 1 to 2, what is happening is this is the refrigeration place. Okay, this is the refrigeration place and this is the surroundings. You can consider like that. So the refrigeration place will have lower temperatures and this outside surroundings will be at higher temperatures. Now here the liquid will get evaporated at lower temperatures in the evaporator. Okay, and that vapor is compressed to higher pressures in compressor. Now as it is compressed to higher pressure, what happens is it will reject the heat. Okay, it will reject the heat to the surroundings which are at higher temperatures. Now as it rejects the heat, the enthalpy get reduces from 3 to 4. Okay, from 3 to 4 the enthalpy gets reduced, and from 4 to 1 the enthalpy remains constant but pressure decreases. So this is the cyclic process that we have discussed previously. Now here if you see here, this line represents the saturated steam line. Okay, this line is representing the, I will erase all the other lines so that it is clear. So this line is representing the saturated vapor line. Now as I compress the liquid from saturated state, it will end up in some superheated state. Superheated means at this point the vapor, it is a completely dry vapor, but now again here it is the temperature is increasing much above the boiling point. That's why it is called superheated vapor. Now the superheated vapor is condensed in the condenser. So in condenser it is rejecting the heat to the atmosphere. Now here this is one diagram and this is another diagram. This diagram is pressure versus enthalpy diagram, and this diagram is temperatures versus entropy diagram. So here you can see the point 1 to 2 is constant pressure process, point 2 to 3 is constant entropy process, and point 3 to 4 is constant pressure process, point 4 to 1 is again constant enthalpy process. But here if I this point, if it is here, then it is corresponds to this diagram. So this is the saturated vapor line, and at this point will compress the vapor and you will get the superheated vapor like this. Now this superheated vapor will get condensed in the condenser from point 3 to 4. So this is the different process. Say suppose sometimes what will happen is you can have a superheated vapor at the inlet itself, and so here the vapor is it is a wet steam. Here it is a saturated liquid, here it is a saturated steam, here it is a wet steam. Wet steam in the sense still some liquid particles are remaining in that, and here it is a superheated steam. So this is about the vapor compression refrigeration cycle that we have discussed in the previous class. Now we have four processes, and how these four processes affect the performance of the vapor compression refrigeration cycle we have to see. Before that, we will see what is the performance. The coefficient of performance. The coefficient of performance. If you remember, we have already discussed coefficient of performance means it is the output by input. So the output by input generally will put as efficiency. So but here in for refrigerations and heat pumps, we call it as the this coefficient of performance, and here the coefficient of performance means the desired effect divided by work input, the desired effect. Okay, desired effect by work input. So what is the desired effect in refrigeration? So here the heat is getting removed from this room, and here the heat is supplied to the atmosphere. So what is the desired effect here? Here the heat that is taken from the refrigeration room is the desired effect in case of refrigeration system. In case of heat pumps, the heat supplied to the room, that is the desired effect. So if I consider the COP of a heat pump, it will be, say suppose this is heat in condenser, then say suppose this is the heat in condenser. Now I can write this as a condenser heat supplied in the condenser divided by omega. I'm sorry, divided by W, that is the net work input in the compressor. Now here this will be more than 1. Okay, efficiency will always be less than 1, but the coefficient of performance can be more than 1, as we can see in the case of the heat pumps. But coming to the refrigeration cycles, the coefficient will be less than 1. And now here the heat extracted or the desired effect, that refrigeration effect produced, is between 0.2 to 1. The enthalpy at 0.2 is more and the enthalpy at 0.1 is less. So the refrigeration effect is H2 minus H1. Now here this refrigerant is vapor refrigerant is compressed in the compressor. So the from enthalpy 2 to enthalpy 3, it is increasing in the compressor. So what is the work input to the compressor is H3 to H1, that is H3 minus H1. Now what is the coefficient of performance? Coefficient of performance is nothing but the refrigeration effect by work input. The refrigeration effect is H2 minus H1 and the work input is H3 minus H2. So this is about the coefficient of performance, how the performance is there, what is the coefficient of performance of vapor compression refrigeration system. Now we will see how these 4 cycles are affecting the coefficient of performance or the performance of the vapor compression refrigeration system. So the first one is effect of suction pressure. So the first one is effect of suction pressure. So what is the effect of suction pressure here? If I reduce the suction pressure, see here, this is the suction pressure. If I reduce the suction pressure, what happens? Or decrease in the suction pressure, what happens? That we have to see. Now the actual pressure is P1 and the pressure now is P1 dash. Now what is the enthalpy here? The enthalpy is the same. It is a H1 dash. H1 or H1 dash both are equal. Now what happens to the enthalpy at 0.2? Now the enthalpy at 0.1 is this. The enthalpy at 0.2 is this. So H2 dash is less than H2. Okay, what is happening? Because I am reducing the suction pressure, the enthalpy at the inlet of the compressor is decreasing. Okay, because of the reduction in the suction pressure, the enthalpy at the inlet of the compressor is decreasing. Now if I, from this point, if I go along a isentropic line, then it will come to a point 3 dash. Now here what is the enthalpy? The enthalpy at the exit of the compressor will be greater than the actual enthalpy. So the before reduction in pressure and after reduction in pressure. So the enthalpy after reduction in pressure is more at the end of the compressor if the suction pressure is reduced. So what is happening here? So this is the COP. Now this is the actual COP, this is the actual COP. Now if I reduce or the original COP, if I reduce the suction pressure, what happens is it is H2 dash minus H1 dash divided by H3 dash minus H2 dash. Now what is this H2 dash? H2 dash so if I want to convert this in terms of H2 and H1, how it will be? Now you can see H2 dash minus H1 dash. How you can split that one? You can split that one since H1 dash is equal to H1. I can directly write H1 dash is nothing but H1. Okay, H1 dash I can replace with H1. Now what I want is H2 dash. So what is H2 dash? H2 dash is nothing but we have a value of H2 minus H2 dash. So what I am doing this, I am subtracting this from H2 dash. So the net effect is similar, same as H2 dash. H2 minus H2 minus this is H2 minus H2 and minus of minus it is plus H2 dash. So if I do like that, what happens is it is coming back to this H2 dash. So this H2 dash is replaced with this term. So we'll end up with this term. So what is happening here? The refrigeration effect. What is happening to the refrigeration effect? This is the original refrigeration effect and it is getting reduced by some amount. This is the amount which it is getting reduced. So the refrigeration effect is decreasing. So the what is happening to the work? So the work, what is happening to the work is, so here this is the original work. So this is the original work and now what we are doing, we are say suppose if I want to replace this H3 with H3 dash, how to do that? Again same thing, H3 minus H3 minus H3 dash. Okay, H3 minus H3 minus H3 dash. If I substitute that here in place of this, I will get this expressed in terms of H3. Okay, if I replace this term with this, I can express this in terms of H3. So if I substitute like that, what I will get? I am substituting H2 dash with this and I am substituting H3 dash with this. If I substitute like that, what I will get? H2 minus H3 minus H2. So this is the first term. Next, what is the next term? It is so here plus H2 minus H2 dash plus H2 minus H2 dash. Why I am getting this? Minus of minus is H2 minus H2 dash. What is the other term I am getting? I am getting here H3 minus H3 dash is there and if I take this minus inside, it will be H3 dash minus H3. Why I am substituting like that? Because H3 dash is greater than H1, H3. So I am replacing, I am changing the notation like that, and again here H2 is greater than H2 dash here. So I am replacing with that. So this is a positive value, this is a positive value, and this is a added to the work input. So the refrigeration effect is reducing as well as the work input is increasing. So the denominator value is increasing, the numerator value is decreasing. So the net effect is the COP of the vapor compression refrigeration system, if I decrease the suction pressure, is decreasing. So we'll have a summary with that. What the previous exercise we have seen, with the decrease in suction pressure, the refrigeration effect is decreased, the work required is increased, the net effect is the COP is decreasing. The COP is decreasing. Okay. So that is the effect of suction pressure. So if you read this statement, the net effect is to reduce the refrigerating capacity of the system. Okay. So this is the same thing they have written in terms of a statement. The refrigeration effect is decreasing as we decrease the suction pressure. Okay. So next we will see what is the effect of increasing the delivery pressure. So here I am increasing the delivery pressure. So increasing the delivery pressure means what I have to do? I have to go along this isentropic line and come to a pressure called P4. This is a P2 now, P2 dash. Now this is P2 dash, and this corresponds to the condenser line, condensation line, and the condensation line is from 4 dash to 3 dash, and now from 4 dash to 1 dash is our throttling or expansion process. So what is happening to H1? H1 is this is H1 and this is H1 dash. So here H1 dash is greater than H1. So the enthalpy at the end of the throttling process is increasing. The enthalpy at the end of throttling process is increasing because of increasing in the delivery pressure. What is happening to the enthalpy at the end of the refrigeration part? It is not changed. At the end of the evaporation, at the end of the evaporation process, the enthalpy is not changed. Now, what is happening to the enthalpy at the end of the compressor process? If I see that this is H3 and this is H3 dash, H3 and H3 dash. So, what is happening to the enthalpy? The enthalpy is increasing at the end of the compressor. So, at the end of the compressor, the enthalpy is increasing, that is H3 dash minus H3 dash is greater than H3. So, the enthalpy at the end of the compressor is increasing. The enthalpy at the inlet of the evaporation process is increasing. So, what is the net effect? How it is affecting the COP? So, this is the original COP. Now, what is the present COP? It is H2 dash, H2 minus H2 dash and H3 dash minus H2. This is the refrigeration effect and this is the work done. So, refrigeration effect is H2 dash minus H1 dash divided by H3 dash minus H2 dash. Now, H2 dash and H2 dash are same because the point is not changing. So, in previous cycle and this cycle, the enthalpy at the end of the evaporator or inlet of the compressor is not changing or it is remaining the same. Now, what I am doing again, I am substituting this H1 dash in terms of H1. How to do that? So, again I am doing the same thing. H1 minus H1 minus H1 dash. I am replacing like this. So, what is happening here? So, this is minus H1 dash. So, minus H1, in place of minus H1 dash, what I have to put? I have to put this entire term. So, I can use this minus here. This will be minus and this will be plus. So H2 minus H1 is the first term. This is the original refrigeration effect. Now what is the remaining term? It is H1 minus H1 dash, but H1 dash is greater. So what I have to do? I have to make it H1 dash minus H1. If I make it H1 dash minus H1, one minus will come and this will be minus. So what is happening? Again, the refrigeration effect is decreasing because this is a positive value and I have to subtract this positive value from the original refrigeration effect. The refrigeration effect is decreasing. So the refrigeration effect is decreasing. So the refrigeration effect is decreasing. So what is happening to the work input? Work input we will see. Now this is the work input. This is the present work input after increasing the delivery pressure. It is H3 dash minus H2. So what I have to do again? I have to put H3 dash is equal to H3 minus H3 minus H3 dash. If I put this like this, what I will get? H3 minus H3 dash minus H2 is there. H3 minus H3 dash minus H2 we have. So what I am doing? I am replacing H3 dash with this term. So if I replace that, what will happen here? H3 minus H2 will come. This is the original work input. Now what is this? Here H3 dash is greater than H3. So again if I if I take the minus here, what it will happen is it is plus H3 dash minus H3. So here this is a positive one. So we are adding some value to the denominator. That means the work input is increasing. The denominator is increasing and the numerator is decreasing, and the net effect is the coefficient of performance is decreasing. So if I decrease in suction pressure or increase in delivery pressure, the effect is same. That is, the coefficient of performance is decreasing. In other words, the performance is going to decrease. So here again we will see the summary. The effect of increasing the delivery pressure is it is similar to the suction pressure. The effect of the increasing in delivery pressure is similar to the effect of decreasing in suction pressure. That what I have said already. The only difference is that the effect of decreasing suction pressure is more predominant. Why it is more predominant? If you recollect, we have two terms in the denominator. So you have two terms in the denominator in case of decreasing suction pressure, and in case of increasing in the delivery pressure, we have only one additional term in the denominator. So the effect of delivery pressure is less than the effect of suction pressure reduction. So what is the next one? So the next one is effect of superheating. So what is the effect of superheating? So effect of superheating means at the end of the evaporator, the enthalpy should be superheated. So H2 must be, this is superheated. So it is H2 dash is greater than H2. Now what is this one? It is H3 dash is greater than H3. H3 dash is greater than H3, as well as H2 dash is greater than H2. So what is happening to the COP again? Now we will see. The original COP is H2 minus H1 divided by, I will write here. So this is H2 minus H1 divided by H3 minus H2. So this is the original COP. Now what is the present COP? It is H3, H2 dash, H2 dash is changing, H1 is remaining same, and what is happening to the H3? H3 is changing. Now what I have to do? I have to replace this H2 dash with H2 minus H2 minus H2 dash. Okay, and I have to replace the H3 dash with H3 minus H3 minus H3 dash. If I replace like this, what will happen here? It will become H3 H2 dash minus H1. So here it is H2 minus H1 and we have H2 dash minus H2. So since H2 is greater, what I can write here is plus H2 dash minus H2. So this is the numerator. What happens to the denominator here? In denominator, it is H3 dash minus H2 dash. If I replace these two, what I will get is H3 minus H2. This is the original work plus, again here I have to minus this side plus H2 dash minus H2 plus H3 dash minus H3. So here what we have seen, what we have done is we have replaced H2 dash with this term and H3 dash with this term, and we got this term. So what is happening here is again the numerator is increasing. So the numerator is increasing as well as the denominator is increasing. So here, even though there is the you can see here the difference, this one and this one, H2 dash and H3 dash. So this effect is little better as the COPE is not reducing drastically, because there is some increment in the numerator as well. Now the last one is effect of subcooling. So what is the effect of subcooling? Now what is the meaning of subcooling? Here already we have liquid. Now if I reduce the liquid pressure, if I reduce the temperature of this liquid further, that is called subcooling. So if I reduce the temperature further, this is the enthalpy. So this is H1 and this is H1 dash. Now what is happening here for about the coefficient of performance? So the original COP is like this. COP is equal to H2 minus H1 divided by H3 minus H2. So what is happening to the COP now? So because I am reducing the temperature of the liquid. So what is happening here? The H1 dash is H1 is becoming H1 dash and H2, H3 are remaining same. So what is the effect? It is much simpler. So what I have to replace? I have to replace H1 dash with H1 minus H1 dash. So if I replace like that, what will happen is H2 minus H1 and here which one is more? H1 is more than H1 dash. So it is H1 minus H1 dash. Here H1 is greater than H1 dash. So I am keeping it as it is. Now this is H2, H3 minus H2. So the denominator is not changing, but the numerator is decreasing. So since the numerator is decreasing, so what is happening is the COP is decreasing. Okay, since the numerator is decreasing, so it is H2 minus H1 minus of H2 H1 minus H1 dash. So here you can see here this is H2, the original one is H2 minus H1 and the other one is H2 minus H1 dash. So this is the original refrigeration effect and this is the present refrigeration effect because after subcooling. So what is happening after subcooling? The refrigeration effect is increasing and what is happening to the work is same. So since work is same and the refrigeration effect is increasing, because of that what is happening? The COP is increasing, the refrigeration effect is increasing but the work is remaining same. Because of that the COP is increasing. So this is these are the few effects of changing the pressures and temperatures of different processes. So what are the four processes that we have seen? Four effects that we have seen. Reduction in subcooling. Okay. So the reduction in subcooling and because of reduction in subcooling, reduction of suction pressure. The first one is reduction in suction pressure. The COP is decreasing and the increase in delivery pressure. Increasing delivery pressure, the COP is again decreasing, but it is not so decreasing as compared to the reduction in suction pressure. The third one is effect of superheating or increasing the temperature of the at the end of the evaporator. Increasing the temperature at the end of the evaporator. So with that what is happening is little bit as compared to the other one, the refrigeration effect is increasing but the work is also increasing, so COP is decreasing. Coming to the subcooling process, here the refrigeration effect is increasing but the work input is remaining same, so the COP is increasing. So these are the four effects of altering the cycles, vapor compression refrigeration cycle. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.